Hello workers, welcome to number 3 of magnetic fields. This time we're going to look at the Earth's magnetic field, sometimes called the magnetosphere or magnetosphere. What do we know about it? Well, the Earth has a magnetic field. The difference between there's a relationship between the Earth's magnetic field and the geographic North and South Pole. And the difference between the spinning geographic pole, so what we would call the North and South pole, where they go and stick their flags and things, and the magnetic axis, so where we think the magnetic North and magnetic South is called the angle of declination, and we'll show you a diagram very shortly that might clear this up. The downward angle of the dip to the Earth's surface is called the inclination. So the magnetic field comes out of the Earth's surface at an angle, and that's the angle there. Or it may go into the Earth's surface depending on where you are in the northern or southern hemisphere, and that's called the inclination. And our actual magnetic poles wander around the surface because the Earth's magnetic field is a very dynamic thing. Well, not as dynamic as say the Sun's magnetic field, but it still is quite dynamic. It can wander, the poles can actually wander, whereas the geographical poles are pretty fixed. The Earth does wobble a little bit, but not nearly as much as the magnetic field wobbles. And the magnetic poles have actually reversed through time. So there's been polar reversals, and we'll talk about that when we talk about some of the things about geomagnetism. So this little diagram out of your textbook shows the idea. There's our north geographic pole and our south geographic pole, and this is our north magnetic pole and our south magnetic pole. And notice that they've drawn, if the Earth's magnetic field was solely due to a great big bar magnet, this would be the bar magnet that generates the Earth's magnetic field, because what they're saying is the Earth's magnetic field is coming out here and going in here. Now, why do they say that? I don't think there's another diagram that says why they think that, but the reason is if we extend this magnetic field line like so, because we've defined our magnets as being the north end is north seeking and the south end is south seeking, and we say that the magnetic field lines come out of the north of a bar magnet and into the south, you can see that this is the direction that the Earth's magnetic field must go. And so if field lines are going in here, if we make an analogous to our bar magnet, alright, field lines go in the south, yep, and come out the north. So if the Earth's magnetic field was due to a big bar magnet, we would need a north there because they're coming out. So here in Australia, let's just do that, and in Tasmania, our field lines are coming out of the ground. And in the northern hemisphere, we would say the Earth's magnetic field lines going in to the ground. Okie doke. Let's get rid of that. Let's get rid of that. And let's move on. Sometimes this pen is quite slow. Anything happening? Okay. So, now what did I say is coming? So this would be Tasmania, and there's our north, and the field lines of the Earth's magnetic field's coming out at an angle, and this is the angle of inclination. And for most of the world it's not a problem, and you don't really notice it. When I was down south in Antarctica, the field lines were coming out at such an angle, much like that you actually had to hold a compass at an angle to get the whole thing to rotate, and then gravity started playing into it, and it all got very tricky. And in fact, lots of expeditions have gone down south trying to find where they can measure the field lines. Whoops, dropped my pen. Where they can measure the field lines coming out of the Earth at 90 degrees, because that would be the South Magnetic Pole, which would be a pretty cool place to go. And contrary to popular opinion, if you held a compass there, it wouldn't just spin around. There's nowhere really on the Earth that happens. So this is a picture of the wanderings of the North Pole. I couldn't find one for the South Pole, but the South Pole has wandered around just as much. But historically, we've got better records over a longer term for the North Pole. So this was year 1000, and you can see that over the years it's wandered around, and it's out there in the North Atlantic at the present time. So it's actually wandering around. Now the magnetosphere is the Earth's magnetic field. Now this is a dire cross section through it, and it doesn't look like a bar magnet magnetic field, because it actually gets distorted. It gets distorted by this guy here, the solar wind, and we're going to have a video learning about the solar wind shortly. And so if you took the magnetic field that would be nice and symmetrical, this solar wind causes it to have this tail, and it becomes this tail is always pointing away from the sun, basically. And then we have these things called Van Allen belts, which we're going to learn about shortly, and they're quite interesting as well. So the Earth's magnetic field is not as simple as a bar magnet. Nowhere near it. It's much more complicated than that. And so, this is the diagram where, of course, we've defined compasses as north-seeking and south-seeking. This is the direction that we give field lines. It doesn't really matter which way the field lines are going. It's just that we've made this convention, and therefore we can draw arrows on them. But in the real world, it doesn't really matter that much. And here's a question: what's wrong with this diagram? Hopefully you spot it straight away. They've got their bar magnet around the wrong way, because they've got the field lines going into the north. The things you find on the internet. So what causes the Earth's magnetic field? Well, here's a very simplistic diagram of the Earth. We have a liquid metal that makes up the outer core, which is 2. We have a solid inner core, and then we have a mantle, which is fluid as well. And what's happening is that this molten core can flow, and because it's flowing and it's within a magnetic field itself, we're generating an electric current because there's charges flowing, and that electric current in the swirling outer core generates a magnetic field itself, and that field is stronger than the very weak magnetic field that is causing the current in the first place. So it's a very complicated process, but basically it's because this is swirling around. Why is this swirling around? Well, because of the heat convention, basically, but also because the Earth is rotating, and there's frictional drag between the rotation rate at the outside and the rotation rate on the inside, and that is the Coriolis effect. And I'm going to show you some, there'll be a whole lot of writing shortly, so make sure you read that. It's a bit twisted, like there's a magnetic field causing a magnetic field causing a current. Basically it's because this is molten and it's got charges and it's swirling around and it's generating a magnetic field, which is the Earth's magnetic field. And this self-sustaining loop is known as the geomagnetic dynamo. So energy is needed to keep the Earth's magnetic field happening. The energy comes from the release of heat from the surface of the solid inner core, and that's because radioactivity is occurring down there, producing heat, and the Earth's acting like a big insulator, so it gets quite hot. And you might think, well, how can you have a solid inner core if it's so hot down there? It's because of the change of state is related to the pressure. There's a massive pressure down there, and so at that pressure, even though it's extremely hot, the rocks that are down there, the materials that are down there, basically it's a whole lot of metals, are solid. If we suddenly release that pressure and kept the same temperature, they'd all melt. But that's why we have a solid inner core. And we get convection cells generated in the liquid core, so it's the liquid outer core that's causing the magnetic field. And here we are, the Coriolis effect also adds to the swirling effect of the outer, what do we call it, the inner core, inner liquid core, not the inner, the molten part of the core. And what have we got here? Spinning Earth makes there. So without the effects caused by the spinning Earth, the magnetic fields generated in the liquid core would cancel one another out, and we would have no distinct north or south poles. We might have a weak magnetic field. Now, how do we know all this? Well, some people are modelling the Earth's molten core. They do this in this apparatus, and they use molten sodium. Sodium's a very reactive metal, so they've got to be very careful, but it flows at relatively low temperatures, so they can look at it. This was the prototype, and then they got bigger, and they swirl it around, spin it around, and measure the generation of magnetic fields. And this is a big version here. I'm not certain if I've found some videos for it. If I have, it's pretty impressive, and I'll put them on the OneNote for you. Other planets have magnetic fields. Jupiter, Saturn, Uranus and Neptune all have magnetic fields, and this is just reinforcing our understanding of the Earth and the cross section of what it's made up of. So we've got iron, nickel in the core, liquid nickel and iron in this part, the outer core, then we've got rock and then rock. But how do we know this? Because we can't drill a hole. The biggest hole we've drilled is about 12 or 14 kilometers, which is only a tiny little blip on this diagram. But we know about the phases of the Earth because we looked at earthquakes, and earthquakes they change, they have phase changes when they go through different transitions from what we would call plastic rock that's molten but still solid, liquid rock and solid rock. And so you have, because some waves cannot travel through a solid, there's a shadow. So if there's an earthquake here, you get a shadow over here, and there's another shadow. There's different types of shadows, and by looking at earthquakes happening all around the Earth, geophysicists can work out the size of these things, and it's pretty well known. Now, how do we know what's actually inside them? Well, that's where the meteorites come from, because most of the meteorites that fall on Earth are from the failed planet that relates to the asteroid belt, and by looking at their compositions, we also got meteorites from Mars and various other places, we can get a pretty good estimate of what the composition of the Earth is. We also get sampling from the upper mantle and occasionally from the lower mantle. And so this is just another diagram going back to our plate tectonics, and just gives you the scale of the different layers. So we really live on this little crusty bit here, but there's a lot more to the Earth that we actually know about. Now, how does the Earth compare to Mars, for example? Mars is a magnetically pretty dead planet, and this is the magnetic field and variations here, whereas Mars doesn't have much at all. This is our profile. Mars has a similar profile but isn't as big, but it's magnetically dead. And when you watch this video, which is Mars magnetic field, that will give you some indications as the difference between Earth and Mars. So in the next video we'll actually look at those Van Allen belts that I mentioned briefly before. So I'll see you then. Bye.